All right, welcome to our Zoom session that's not really a Zoom session. I mentioned this in the email I sent you. Section 5.5 is due on a Wednesday, so just heads up on that. Put it on your syllabus so you remember. Um, Midterm is on Monday at 9, and then I sent you a link for optional office hours this Friday. Today we're going to go through mostly some setups. Um, I'm going to find two double integrals for the area of this region. This is the region bound by y equals 1/9 x squared on the bottom and y equals 1 on the top. Okay, and so the top boundary is 1. The bottom boundary is g of x equal 1/9 x squared. And so if we're thinking of this region as made up of little vertical lines, the area of this region would be the double integral. Y goes from, those lines enter the region at 1/9 x squared. They leave when y is 1. X goes from 1 to 3 because when x is 3, 9 over 9 is 1. So, sorry, x starts at 0, goes to 3. And then if we integrate the function 1 dy dx, we'll get the area. All right, the other way to look, so this part, the interval of x values that the region covers goes from 0 to 3. We can also think of this region as made up of horizontal line segments. In this case, we're going to have a left boundary and a right boundary. So the left boundary is 0, that's the y-axis. The right boundary is, we need to solve this equation y equals 1/9 x squared for x. So x squared is 9y, so x is 3 root y. Since we're in quadrant 1, everything is positive. So that's the right boundary. And then the y values go from 0 to 1. So in terms of area, that would be double integral. X starts at 0 and it goes to 3 root y. And then y goes from 0 to 1 dx dy. So the options are a dy dx setup or a dx dy setup. Dy dx is vertical lines and dx dy is horizontal lines. Okay, next one, y is 4x and y is x squared plus 3. Describe the region for type 1 and type 2. So type 1 is vertical lines first. And so let's see. I've already given us a little sketch of the graph here. This is the parabola down here is y equals x squared plus 3. And then when we do the horizontal lines first, we're going to solve for x. So if you solve for x, you get root y minus 3. This is the line up here, y equals 4x, and we'll also need it in the form x equals y over 4. Now, to find out where these curves meet, we're going to set y equal to y to get x squared plus 3 equals 4x. So x squared minus 4x plus 3 is 0. So that's x minus 3, x minus 1 is 0. So they meet when x is 1 and when x is 3. We're also going to need to know where they meet on the y-axis. When x is 1, put 1 into either one of these equations. Y is 4x or y is x squared plus 3. Y is 4x is easier, so this would give us 4 here. And then put 3 in, and this would give us 12 up here. So if we go with vertical lines first, x goes from 1 to 3, and y goes from this x squared plus 3 to 4x. So the area would be double integral x squared plus 3 to 4x, 1 dy dx, x goes from 1 to 3. Or it will be 1 dx dy, x goes from y over 4 to the square root of y minus 3. And we have those horizontal line segments for y going from 4 to 12. So that's how you would fill these in. This would be 4, that would be 12, y over 4, square root of y minus 3. So those are the two area setups. Okay, next one, I'm going to do the setup, but I'm going to start the integration just to remind you of how I want you to integrate. Find the integral of 4x ln y dA, where a is going to be dy dx or dx dy. We have to decide which would be better by looking at the geometry of the region. So let's graph this. Y equals x looks like this. X equals 0 is the y-axis. Y equal 1 looks like that. And y equal 9 looks like that. 9, 1. Y equals x. So we don't want to do vertical lines because then the bottom curve changes halfway through and we need two separate double integrals. If we do horizontal line segments, we can get away with one double integral. So we're going to go dx dy. So we're going to go double integral 4x ln y dx dy. X goes from 0 to y, and y goes from 1 to 9. So I'm going to start the integration. Just to remind you, we're going to do the numbering system in this class. So the inside integral you have to do first, and yes, you have to number it, 0 to y, 4x ln y dx. ln y is constant, so this is 2x squared ln y between 0 and y, which is 2y squared ln y. So integral 2, which I'm not going to do, goes from 1 to 9, 2y squared ln y dy. That's integration by parts. And you can fill that in. You should get 906 eventually. Okay, so next one, we're going to do polar. So this is section 5.3. We're going to set up in both rectangular and polar. Then I'm going to do the polar integral with you. So we want to integrate x dA, where D is over the region D. D is the triangle bounded by y equals x, y equal 5, that's up here, and the y-axis. So this is our region here. Well, actually, they're calling it D. I don't care what you call it. Let me erase that. Get a D. All right, so I'm going to set this up as a dy dx, but then I'm going to switch to polar anyway. So we want double integral of x dy dx. Y goes from, the bottom curve is x, the top curve is 5, and x goes, you're going to have those vertical lines for x going 0 to 5. Okay, now if we want to switch to polar, thinking of this as a polar region, the line y equal 5 is r sine theta equal 5, which is r equals 5 cosecant theta. So r is going to start at the origin and go to the line 5 cosecant theta. So it's going to be, so I replace the x with r cos theta, replace the dy dx with r dr d theta. There's an extra r you pick up when you integrate in polar. You have to watch my video for that, but trust me, there's an extra r. And then r goes from 0, which is the origin, to the line 5 cosecant theta. And then for what thetas do we have those rays going through the region? Well, they start on this line, which corresponds to theta equals pi over 4, and they end on the positive y-axis, which is pi over 2. So that's our setup. So integral 1, 0 to 5 cosecant theta r squared cos theta dr. So you combine the two r's to get r squared. That's 1/3 r cubed cos theta between 0 and 5 cosecant theta, which is 125 over 3 cosecant cubed theta cosine theta. Okay, I could switch all to sines and cosines, but I'm not going to do that. I'm going to switch to cosecants and cotangents for integral 2. I'm going to integrate from pi over 4 to pi over 2. I've got 125 over 3, and then I'm going to write this as cosecant squared theta times cotangent theta. The reason why I want to do that, because now it's an easy U sub. The derivative of cotangent is negative cosecant squared. So U is cotangent, du is negative cosecant squared. So this is going to be, yikes, running out of space, negative, I'm going to take the 125 over 3, pull it out, the integral of u du, and then let's change our limits. Cotangent of pi over 4 is 1. Cotangent of pi over 2 is 0. So that's, I could switch the limits and make that positive, but I'll just integrate it the way it is. That's 1/2, so I get negative 125 over 6 u squared between 0 and 1, which is going to give me positive 125 over 6. You have a lot of them where you're going to integrate powers of sine and cosine, or secant and tangent, or cosecant and cotangent. So I just wanted to do that with you. Okay, the other ones we're just going to do setting up integral of y dA. And so now look at this. We have another triangle. It's almost the same as question 5. X dA and D was this triangle. Now we go y dA, but it's a different triangle. Y equals x, the x-axis, and x equals 5. So this is the line. Think of R as starting at the origin and emanating out. R is going to go, so with double, I'm going to go straight to polar. R is going to go, I'll show you rectangular too, but R is going to start at 0 and go to this line, which is R cos theta is 5, which is R is 5 secant theta. 5 secant theta. Y is R sine theta, but then we'll have R dr d theta. So that'll be an R squared dr d theta because of that extra R. Theta is going to go now from 0, positive x-axis, to this line, which is pi over 4. So that's going to be the polar setup. And again, you're going to integrate, and this time you're going to have powers of secant and sine. So you'll be able to write it as secant squared times tangent. For the rectangular setup, for rectangular, I always go dy dx if given the choice. So we're integrating y, dy dx. Y goes from 0 to x. Oh, sorry, I'm erasing instead of 0 to x. And then x goes 0 to 5. So pretty simple to do in rectangular, actually. Okay. And then next one, we're just going to do the setup. Got two paraboloids, elliptical paraboloids. One opens up, one opens down. And I replaced in each of these, I took x squared plus y squared and I replaced it with r squared. So the one that opens up is negative 8 plus r squared. The one that opens down is 4 minus 2r squared. So the volume is going to be double integral of top minus bottom dA over the region where they meet. So we have to find out what region that's going to be. So to find out where these curves meet, surfaces, sorry, we're going to set z equal to z. We're going to see they meet over a circle. Set z equal to z. So 4 minus 2r squared equals negative 8 plus r squared. That gives me 3r squared is 12. R squared is 4. So they meet over a circle of radius 2. R equals 2. Remember, we keep r positive in polar coordinates. So they meet over a circle of radius 2. So this is going to be top minus bottom, leave that blank, r dr d theta. R is going to go from 0 to 2, and we want to go all the way around the circle. So theta goes from 0 to 2 pi. Now we have to put in top minus bottom. So the top is 4 minus 2r squared, and then subtract off the bottom negative 8 plus r squared. Because these surfaces only meet, so let me try and draw a better picture. These surfaces meet in the xy plane over a circle. Well, it's actually centered at the origin, sorry. They meet in the xy plane over a circle of radius 2. So if you're integrating top minus bottom in polar, you just need a polar let's see. We haven't really talked about cylindrical coordinates yet. Let me pause this. I think this will make more sense when we do cylindrical coordinates. However, think of it as setting this up in rectangular coordinates. And then once you have the integral in rectangular, switching it over to polar. So I'll show you the rectangular setup too. But let me just first, once you're ready to integrate, this all has to get simplified. This is going to be 12r, right? Because it's 4 minus negative 8 is 12, and then you're going to multiply by r. So 12r, and then minus 3r cubed. So that's what you're integrating. So if you were setting this up in rectangular coordinates, this is exactly what you'd do. You'd set z equal to z, but instead of having polar, you'd go negative 8 plus x squared plus y squared equals 4 minus 2x squared minus 2y squared. And then you get x squared plus y squared equals, I'm adding 4. So again, that's a circle of radius 2. The bottom of the circle would be y equals negative the square root of 4 minus x squared. The top is y equals positive the square root of 4 minus x squared. And x would go from negative 2 to 2. So the rectangular setup would be double integral. X goes negative 2 to 2. Y goes from negative the square root of 4 minus x squared to positive the square root of 4 minus x squared. dy dx. Top curve was 4 minus 2x squared minus 2y squared. And then the bottom curve is negative 8 plus x squared plus y squared. Okay, and then if you simplify that integrand, negative 2 to 2, negative square root of 4 minus x squared to square root of 4 minus x squared, you get 12 minus 3x squared minus 3y squared. So 3x squared plus y squared. dy dx. So I actually just saved a step. When you do this setup, then you want to convert to polar in order to integrate. And the rules for converting a rectangular to a polar are: one, everywhere you see an x, you replace it with r cos theta. Everywhere you see a y, you replace it with r sine theta. Or everywhere you see an x squared, you replace it with r squared. So here's our 12 minus 3r squared. And then replace dy dx with r dr d theta. So there's that extra r that we're seeing in 12r minus 3r cubed. Then you need to completely change these limits to the polar limit. So for a circle of radius 2, the polar limits are theta, r goes 0 to 2, theta goes from 0 to 2 pi. So it's actually an easier setup in polar. All right, last one. Evaluate the integral over the region R. So I'm just going to set it up with you. And we're going to sketch the region. So this is R squared going between 25 and 9, which is R going between 5 and 3. R equal 3 is a circle of radius 3. R equal 5 is a circle of radius 5. X is less than or equal to 0. So we're getting, erase that. We're getting this, it's like a lifesaver or a bagel, and we're getting the left half. Okay, so how would we set that up in polar coordinates? First of all, the 9x plus y is going to become 9 r cos theta plus r sine theta. The dA will become r dr d theta. And now how to describe this region in polar? Well, r is going to go, if we imagine rays emanating from the origin going through the region, r is going to start at the origin, doesn't hit the region till 3, and it leaves the region at r equal 5. And then for what thetas do we have the rays going through that region? Well, they start at pi over 2 and they go to 3 pi over 2. So there's the setup for polar. And when you integrate, remember, first you distribute. So it's going to be 9r squared cos theta plus 9r squared sine theta dr d theta. And then I did this earlier, and then I got negative 588. So you can go through, make sure you get that as your answer. So that was it for what I had. There's two good ways to study for your midterm. One is the practice midterm. You know that's really super important. And then two is in the double integral and in the polar integral, I had a worksheet at the end, the practice sheet. Definitely do that practice sheet because it'll be a good practice for looking at a region, looking at an integral and deciding, oh, what does that look like? How can I sketch that region? And then convert it to a polar integral. So that'll be good practice. Okay, and that's it. So I'll either see you on Friday at office hours or I'll see you on Monday at the test.